Okay, so I'm going to make a couple of videos here for Math 122, where I'll solve some of the homework problems in the course notes, and maybe talk about some stuff from quizzes and stuff like that. This is to make up for the fact that I'm not doing office hours this week. I thought I would start with chapter 4 on induction, because I think a lot of people are not really understanding how induction works, and in particular, the difference between strong induction and weak induction, when you should use one or the other, and things like that. So let me actually write down a few different examples of some induction questions. Some of these are from the course notes. One of them will be a kind of different question that's not in the course notes. And let's kind of just talk about for which of these questions we need weak induction, or we can get away with using weak induction, and for which problems we need to use strong induction. So for the first question, we're asked to prove that 4 to the n minus 1 is a multiple of 3 for all n at least 0. So that is question 7 from chapter 4. So specifically from section 4.12, which is the exercises of chapter 4. For the second question, we let t0, t1, etc. be defined by in the following way. So t0 is equal to 1, t1 is equal to -4, and tn is equal to -4 times tn minus 1 plus -4 times tn minus 2 for all n at least 2. So this defines a sequence in a recursive way, and you are asked to prove that tn is equal to -2 to the n plus n times -2 to the n for all n at least 0. Okay, the last question, which doesn't come from the course notes, but it's just a nice, interesting question. It says to prove that every positive integer n can be written as a sum of distinct powers of 2 with integer exponents. So as an example here, we can say that 3 is equal to 2 to the 0 plus 2 to the 1. Or for example, 11 is 2 to the 0 plus 2 to the 1 plus 2 to the 3. And I want to show that every integer can be written in this way. So now for each of these questions, what I would ask you to do right now is think about two different things. So first of all, how many basis cases do you need for this problem? Okay, and what do I mean by need? Well, basically, you know, for any integer n for which you cannot prove the statement by kind of recursively looking back at a previous value of n, if you need to do that value of n by hand, then you need that to be a basis case. Okay. Now it takes practice to learn how many basis cases you need, but it's something that comes with practice. So I really recommend doing a lot of these, and then you will get a feeling for how many basis cases you need. The second question I have for you is, should you use weak induction or strong induction? And specifically, I want to know which one will work for each of these questions. Okay, so that's what you should think to yourself now. So try to work it out for yourself, and then I will tell you the answer. And to be clear, you should think about this for all three of these questions. Okay, for the first question, prove that 4 to the n minus 1 is always a multiple of 3 for all n at least 0. Well, to be honest, this one is not so obvious immediately before you see the trick for how to solve it. But in this case, it turns out that only one basis case is needed. So only one basis case is needed for the first question. But importantly, I understand that when you start solving it by induction, you may not know how many basis cases you're going to need. I mean, especially if you're under time pressure, um, and you're kind of trying to do this quickly, you may not be able to think deeply about the structure of the proof and exactly how many basis cases are needed in advance of solving the problem. But here's the thing, you don't have to do that. I mean, you are allowed to do more than one basis case, even if you only need one. So if you are in this kind of situation, then it's okay for you to do a few, maybe 2 or 3 basis cases. You'll probably never need more than that. But just to be safe, you might want to do a few basis cases just to make sure you're going to cover everything you need to do, and then you can move on with the inductive hypothesis and the inductive step. But just to be clear, like, you only actually need one. If you think about how this proof is going to go, one basis case is enough, but you can use more if you need to. So now regarding the question of whether to use weak induction or strong induction, again, if you don't already know how this proof is going to go, you might not be able to determine which one you need. But in this case, if you think about how the proof is going to go, if you know how it's going to go, you'll probably be able to see that weak induction is all you need. So you don't actually need strong induction, but it's never wrong to use strong induction. As long as you do it correctly, anything that can be proven with weak induction can also be proven with strong induction. So unless you're told specifically to use weak induction, you're always allowed to use strong induction if you want to. Okay? The only benefit of weak induction is that it's a little bit simpler to formulate. It's the inductive hypothesis is like simpler to write down. It has those advantages, and so therefore there's kind of less chances for making mistakes because it's just a simpler way of writing things down. But it's very important that, so there will be some problems where you have to use strong induction, and then using weak induction will be wrong, but the opposite never happens. So it's never the case that you have to use weak induction. Anything that can be proven with weak induction can also be proven with strong. Now let's look at the second question, number 11, or sorry, number 12. So now let's look at the second question, number 12 from chapter 4. And let's ask ourselves the same questions. How many basis cases? And can you use weak induction? And in this case, the answer is going to change, okay? Here's the thing. You need 2 basis cases in this proof, because if you look at the definition of the sequence, T0 is just defined to be equal to the number 1, and T1 is equal to -4. So therefore, for example, if I wanted to if I wanted to prove something about T1, I cannot use information about T0 to prove something about T1, because T1 is not defined in terms of T0. It's just not. It's just defined to be -4. And so basically, T0 and T1 need to be treated separately outside of the induction. Therefore, they must be the basis cases. However, if you think about it, what about T2? Well, we have this formula that T2 is equal to -4 times T1 minus 4 times T0. And that kind of allows us to figure out something about T2 by knowing information about T1 and T0. So therefore, basically, T2, T3, etc., can be dealt with using induction by kind of looking back at the previous 2 values, because each Tn is defined for n at least 2, each Tn is defined in terms of the previous 2 values. But for T1 and T0, it's not defined that way. So you cannot use previous information to get information about T1 or T0. But now, similarly to the previous question, when I ask how many basis cases should you do, for example, like you have to do at least two. You have to do at least two. Okay. There is no, you can't get away with doing just one. But if you want to know how many should you do, well, to be honest, two is the best answer because why would you do more work than you have to? But if you wanted to do three basis cases, nothing wrong with that. If you want to do four basis cases, if you want to do 500 basis cases, there is nothing mathematically wrong with that. It's just kind of a waste of your time. But as long as you do two basis cases at least in this question, and specifically the basis cases T0 and T1, maybe I should highlight this. If you start by doing T1 and T2, for example, then that will not prove the statement. You need to start at T0 because otherwise you will never prove the statement for T0 and your proof will be incomplete. So I would recommend doing T0 and T1 and then doing all of the other cases by induction, okay? But like I said, if you want to do more basis cases, just feel free. It's just kind of a waste of your time, and I don't know why you would do it. But like I said, you can't always tell how many cases you'll need, so it may be a safer option. I should say maybe that in these questions, like you've seen a lot of these kind of sequence questions, they're all kind of the same, right? Your basis cases are the cases that have been like written out specifically, like T0 equals 1 and T1 equals 4. And then all of the other cases are just done by induction. Okay. Once you've done a few of these questions, they're all the same. So continuing to talk about question 12 now, do you need to use strong induction? Or can you just use weak induction? Now, in some sense, you don't need the full strength of strong induction for this problem, but you do kind of need strong induction in some sense. Here's why. Here's my question to you. If I know the value of Tn minus 1, only Tn minus 1, does that determine the value of Tn? Can I use the information just about Tn and nothing else to tell me properties of Tn? And the answer is no, because the formula for Tn involves Tn minus 1 and Tn minus 2. So in order to get information about Tn, I need to go back 2 steps. Okay, and that's a signal for you that you should probably use strong induction, because what weak induction does is you want to prove the nth case of the statement. It allows you to look back 1 step and use the n minus 1 case to prove the nth case. In this case, we need to look back 2 steps. So just use strong induction, okay? You've done a lot of these before. You've had a lot of practice. There's a lot more that you can practice. There's a lot of examples in the notes. Just get really good at this. Use strong induction. So now if we look at the third example here, what's going to turn out to happen is that actually this example can be done with just one basis case, just the case n equals 1. Again, it's not obvious to see this before you actually start trying to do the proof, but once you start thinking about it, it does start to become clear that there's not going to be any real value in dealing with more than one basis case. And so you can just, well, I mean, in this case, you can just get away with one basis case. For the second question about whether to use strong or weak induction, the thing to think about, well, so once again, if you can use weak induction, you can also use strong induction. So therefore, there's not really any loss in doing strong induction as long as you do it right, okay? The only difficulty with strong induction is that it's a more complicated argument to write down. The logic of it is a bit complicated, and so therefore a lot of people do it wrong. So that's the only reason why weak induction might be useful in a lot of cases. However, in this case, you can't use weak induction. It will not work. So you do need to use strong induction. Now, let me try to explain a bit of intuition about why that's the case. If I was trying to do this with weak induction, I would have some positive integer n, and then I would go back one step and look at n minus 1 and say, is it possible to write n minus 1 as a sum of powers of 2, distinct powers of 2? And of course, it is possible by induction, by the inductive hypothesis. And so I would take an expression where I write out n minus 1 as a sum of powers of 2. But here's the thing. That sum of powers of 2 may not be useful for expressing n as a sum of powers of 2. So for example, think about n equals 4. As we've seen, 3 is equal to 2 to the 0 plus 2 to the 1. I would like to say that I could just add 1 to that and get 4, which is true, but this will not be a sum of distinct powers of 2, because if I add 1 to this, that's like adding 2 to the 0, and now my powers of 2 are not distinct, okay? So actually, in reality, the way to do 4, n equals 4, is to just take 2 to the 2, but basically, if I was dealing with the number 3 and trying to get an expression for 4, basically the expression for 3 would not be useful. So what I really want to do is look at, assume all of the previous cases are true and try to use that to get the next case. Okay, as it's going to turn out, that's a more useful way to do it. Okay, let's actually prove some of these things. So let's prove the first question. And I'm going to start by doing this by weak induction, and then I'll do it with strong induction, and then hopefully you can see the difference. Okay, first let's do this by weak induction. Let's start with the basis. So what I want to write is let n be equal to, well, what do you think? I mean, what should be the basis case? So if you said that the first basis case should be n equals 0, because that's the first case that we need to prove, you'd be right, okay? So basically, if I want to prove, a statement for n equals 0, 1, 2, 3, blah, 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 where should you start? Start at the beginning, right? Start at n equals 0, and that should be your first basis case. Now, if the statement you're trying to prove starts at n equals 1, then that should be your first basis case, right? It all depends on the question you're trying to solve. Okay, so the next thing we need to do is to remember, what are we trying to prove? We are trying to prove that 4 to the n minus 1 is a multiple of 3. Okay, so, I mean, what I have to do is compute 4 to the n minus 1 for this specific value of n equals 0. And I need to demonstrate that that is a multiple of 3, and then I will have proven the case n equals 0. So let's compute 4 to the 0 minus 1. So 4 to the 0 is equal to 1. Therefore, 4 to the 0 minus 1 is 0. And now we ask ourselves, have we proven it? And the answer is no. I mean, we haven't proven anything. We just computed 4 to the 0 minus 1. We have of 3. So let's express 0 as a multiple of 3. Now, of course, 0 is just 3 times 0. And so that is what we need to show. And so now we can conclude that when n is equal to 0, 4 to the n minus 1 is a multiple of 3. Okay, so you always have to remember, what are you trying to prove, right? And then you have to prove it in the basis cases, okay? Now comes to the part that a lot of people mess up, which is the inductive hypothesis. Okay, so what you need to remember is, what is the inductive hypothesis? For the inductive hypothesis, I want to start with some case of the statement I'm proving. So let's say the nth case, and we're going to assume it's true. And then in the inductive step, we're going to prove that the n+1th case of the statement is true. Okay? Now here's the thing. If I'm allowed to assume something, I'm only allowed to assume something is true if it actually is true. Because if I assume something's true and it's actually false, I mean, what am I doing? I mean, it doesn't actually, it's not useful for anything. So here's the thing. Right now, I know that the case n=0 is true, so I can assume it. And then after we've proven the case n=1, we can assume the case n=1. And basically, what I'm going to do is I'm going to set up my inductive hypothesis to start at the last case that I know is true, which is n=0. And we're going to assume the nth case where n is at least 0. And then in the inductive step, we're going to prove the n+1th case. So the way my inductive hypothesis works is it should say let n be at least 0, which is the largest case that I currently know is true, and assume the statement is true for that value of n. So let me show you what it should say. So specifically, it says let n be at least 0 and assume that 4 to the n minus 1 is a multiple of 3. Okay? Now, the way I've written this, I mean, there's more than one way to write a correct inductive hypothesis. There are many ways to do it, but you have to just do it right. I mean, you have to just be saying the right types of things. Now, let me show you some bad examples. And let me try to explain to you why those examples are bad. So the first example of a bad inductive hypothesis is the following. It says, assume that 4 to the n minus 1 is a multiple of 3 for all n at least 0. This is not good. I mean, the thing is, and let me say, a lot of people have written this. If you've written something similar in your quizzes or assignments, you're not alone. But everyone who writes this gets a 0 on their inductive hypothesis, a 0, okay? It's not even close to correct. It might feel to you like it's similar to the statement that I wrote, but it is not similar, okay? The problem is that you have written that you're assuming the thing that you want to prove. You need to prove that 4 to the n minus 1 is a multiple of 3 for all n, and you're just saying, okay, assume it's true. But if you're already assuming it's true, how can you prove it? Like, it's kind of like saying, I'm just going to assume that it is possible to fly to the moon, and therefore we can do it, right? But I mean, that's not how things work, right? If you want to demonstrate that something is true, you have to actually do it, right? So this inductive hypothesis is bad, very bad. Here's the difference between the one I wrote and the bad one. The one I wrote is just assuming the statement is true for one value of n. For example, n=0. Okay. Which, by the way, we already know it is true for n=0. So there's nothing wrong with assuming it is true for n=0. And the way induction works is that by assuming n=0, the n=0 case, we will prove the n=1 case using that information. And now once I know n=1 is true, I can assume it because it's true. And then using that, I prove n equals 2. Then I can assume it. And then I use that to prove the case n equals 3. And then I can assume it. But nowhere in that process should I ever write assume it's true for all n. Because if you just assume it's true, you haven't proven anything, right? You need to prove it. Okay, so this second inductive hypothesis does look very similar to the one that I wrote. The only difference is that it's saying that we're assuming 4 to the n minus 1 is a multiple of 3 for some n at least 1. That can't quite work, right? Because, we haven't proven the case n equals 1. If in your basis you prove the case n equals 1, then that's okay. Then this inductive hypothesis is correct. However, if I only prove the case n equals 0, then I cannot assume the case n equals 1 yet, because I don't know if it's true. I can only assume the case n equals 0. But then if I use the n equals 0 to prove n equals 1, I can assume that now. And then I can assume it and prove n equals 2, and then assume that and prove n equals 3. And that's how induction works, right? Weak induction, you prove one case at the beginning, you then build on it to get the next one, the next one, the next one. And for every step, you can assume the previous case is true because you've actually proven it. Okay, so these are two bad inductive hypotheses. Let's now do the inductive step. Okay, so now in the inductive step, what are we trying to show? Well, in the inductive hypothesis, I'm assuming it's true for some value of n. In the inductive step, what I want to do is prove that it's true for the next value of n, which would be n plus 1. What comes after n? It's n plus 1. So here's how I'm going to do it. I'm going to start by writing out 4 to the n plus 1 minus 1. And now I need to think about this. How can I show that this is a multiple of 3? And frankly, it's not that obvious. But there is a hint, if you look into the exercises, that kind of should help you. But let's just kind of try to reason it out ourselves. So the thing is, I know that 4 to the n minus 1, sorry, yeah, 4 to the power n minus 1, I know that that's a multiple of 3. So I want to sort of incorporate that somehow into this problem. So the question then becomes, I've got a 4 to the n plus 1. How can I make that look like a 4 to the n? And the way I can do that is by just factoring out a 4. And then let's see what happens. So 4 to the power n plus 1, I can write as 4 times 4 to the n. If that doesn't look okay to you, you do need to really understand your rules of exponents. So this is kind of a standard thing. So now what I'm going to do is I'm going to take that 4 and replace it with a 3 plus 1. The reason I want to do this is because I want to get 4 to the n minus 1 kind of isolated here. And right now, my 4 to the n is being multiplied by a 4. I would rather it was multiplied by a 1. This is going to help me do that. So I'm going to replace the 4 in front of the 4 to the n with a 3 plus 1. Okay, and now let's expand this and see what we get. Okay, so what we get is a 3 times 4 to the n plus 4 to the n minus 1. And now we are in good shape because I can use the inductive hypothesis. The thing is, I have a 4 to the n minus 1 here, and I know that that's a multiple of 3. So by induction, I can replace the 4 to the n minus 1 with a 3k for some integer k. So let me show you how to write that. So what I'm saying here is that by the inductive hypothesis, there exists a k in the integers such that 4 to the n minus 1 is equal to 3k. And why is that true? Well, it's because 4 to the n minus 1 is a multiple of 3. And what does that mean? It means that there exists a k such that that number is equal to 3 times k. That's what it means to be a multiple of 3. Now, finally, I can just substitute that back in to my original expression, the one that I wrote above, and then factor out a 3, and then I'm going to win. So here we go. So I write that 4 to the n plus 1 minus 1 is equal to 3 times 4 to the n plus 3k, because that's just substituting 3k for 4 to the n minus 1, which I can then factor out a 3 and write it as 3 times 4 to the n plus k. And now I'm done because 4 to the n plus k is an integer, and therefore 4 to the n plus 1 minus 1 is a multiple of 3. Okay, so now final thing to do, just write a conclusion and say what you proved. Now, this should never be hard, okay? I know, I'm sure a lot of you have lost marks on this in the past, but I'm telling you, you should never lose marks on this. All you have to do now is write down, what did you prove? Which is pretty much the same thing as down the question. So what I'm going to write is that my conclusion is 4 to the n minus 1 is a multiple of 3 for all n at least 0. That's all. Do not write, there's no reason to write anything else. You don't have to write since the basis cases are true and since induction and since the inductive hypothesis implies the inductive step, and since, like there's a lot of things that people write, and there's no point in writing any of that. Please, for your conclusion, just write what you proved, not how you proved it. Just write what you proved. Basically, if you write a lot of extra stuff here and some of it is wrong, you're just going to lose marks and you're going to waste time on your exam. So why would you write a paragraph of stuff for your conclusion when all you have to do is just write what you proved? Now, like I said, for this question, you can use strong induction, okay? Now, let me tell you how it would change. Everything would be exactly the same as what I've written here, except the inductive hypothesis would need to change. So in a strong induction, your assumption in the inductive hypothesis is that all of the previous cases are true, not just one previous case. So in my induction hypothesis over there, I've written, I assume that 4 to the n minus 1 is a multiple of 3 for some one specific value of n. In a strong induction, that should change to say that the statement is true for all numbers from 0 up to n. Okay, so here's how it would look. So the way it would look is it starts the same. I let n be at least 0. Again, 0 is important here because that is my last basis case. And then what I'm going to say is assume that 4 to the k minus 1 is a multiple of 3 for all k between 0 and n. Or in other words, for all k such that 0 is less than or equal to k, which is less than or equal to n. So that just means all k between 0 and n. Now, I'm allowed to do this, right? Because initially, I've proven the case n equals 0. And now, therefore, I know that it is true for all k between 0 and 0, because I proved the case n equals 0. So it is true for n equals 0, which is the same thing as saying it's true for all k such that k is between 0 and 0. Then I use that case to prove the case n equals 1. And now I can assume that it is true for all k between 0 and 1, because I've proven the case 0, the case n equals 0, and the case n equals 1. So it is true for both of those values. So I know that there's a lot of confusion about the roles of the letter N and the letter K in an induction proof. And let me say, there are different ways of writing a correct proof. Okay. And it doesn't really matter what the variables are called. It just matters what they are doing. Okay. In this proof, the K is only a sort of temporary variable, and all it is doing is communicating the fact that the statement is true for all integers between 0 and n. So K is just something that temporarily communicates this fact. When I go to the inductive step, do you see any K's in the inductive step? The answer is no, and you shouldn't, because there is no K outside of the inductive hypothesis. Once I've left the inductive hypothesis, the variable K it no longer exists. Okay, there is no K after the inductive hypothesis. So I know that the course notes often use the variables n and k in a different way than I've done in this proof. And there's actually nothing wrong with that. The, the names of the actual variables aren't really important. The really important thing is what they're doing. The thing is, I know that it is difficult because induction is new for you. And so a lot of you are probably just trying to follow the pattern of an induction proof. And so when you see it done differently in different situations, it can become confusing. But what I would really suggest is to try, if you can, to not just try to follow the pattern of an induction proof and just learn how to do it and just try to repeat it over and over. What I would really suggest is to understand what induction is, why it works, and if you can do that, which I have to say it's not easy, but if you can do that, then you'll never be confused by any induction proof for probably the rest of your life. That being said, I know that it might be a bit ambitious to do that before the exam, and but you know, if you can't do that, then maybe the best thing to do is just do a lot of these and practice them, and eventually you'll get the pattern for how these things work. So let's work on trying to prove this second question. So just to remind you, t0 is equal to 1, t1 is equal to -4, tn is equal to -4 times tn minus 1, -4 times tn minus 2 for all n at least 2. And our goal is to prove that tn is equal to -2 to the power n plus n times -2 to the power n for all n at least 0. Now, before you can even try to solve this, you need to understand what it means. I mean, so a kind of important question here is, do you understand how the sequence T0, T1, T2, etc. is being defined? Like, do you understand what the question is asking? So let's go through just the first few values of Tn and see how this recursive definition tells us what Tn is equal to. So first of all, T0 is equal to 1. We were just told that in the question. Next, T1 is -4. Again, that's just told to us in the question. Now, when I want to compute T2, well, what is it equal to? The question tells me that the definition of T2 is that it is -4 times T1 minus 4 times T0. So let's compute that. It is -4 times -4 minus 4 times 1. If you put that together, you see that it is equal to 12, because it's 16, positive 16 minus 4 is equal to 12. Okay, next one, T3 is -4 times T2 minus 4 times T1. How do I know that? It's from the recursive formula. And so that's -4 times 12 minus 4 times -4. And in total, what you end up with is -32. Okay. So by the way, all of these calculations I'm doing, this has nothing to do with the proof. You do not have to make these calculations. It's completely as far as the proof goes, none of this is necessary, but this is necessary if you want to understand what you're doing here. Okay. If you want to understand what this question is asking, you need to know how to compute Tn from the recursive formula. Okay, let's look at let's just kind of do a sanity check to determine if this statement looks correct. So let's compute this the right-hand side of this formula, -2 to the n plus n times -2 to the n for each n equals 0, 1, 2, and 3. And if you do that, in the case n equals 0, you get 1. In the case n equals 2, sorry, n equals 1. If you plug in the numbers, plug in 1 everywhere, you get -4. For n equals 2, again, like as expected, you get 12, and then for n equals 3, you get -32. So therefore, it looks like the formula is probably correct, but this is not a proof, right? This is just computing a few values and seeing, okay, it looks okay. But in some sense, if you were doing an exam, you should not do this because there is no point in this, right? You should just try to prove the statement because, well, otherwise you're just kind of spending time doing a bunch of computations that don't actually help for doing the proof. But this is important if you want to understand what you're doing. Okay, so let's actually jump into the proof. We're going to go by strong induction on n. What's the basis? Well, like I said, the basis should be the cases n equals 0 and n equals 1. So I'll start by supposing n equals 0. And now I want to prove that this equation is true. So I'll compute the left side and I'll compute the right side, and I will observe that they're the same. Okay, so what do I mean by the left-hand side? I mean, take the equation you're trying to prove, which is Tn equals -2 to the n plus n times -2 to the n. Left side of that is Tn. Plug in n equals 0, you get T0, which is 1 by definition. The right-hand side is -2 to the n plus n -2 to the n. Plug in n equals 0, gives you 1. So therefore, the left-hand side and the right-hand side of the equation are both equal to 1, and therefore the statement is true for n equals 0. Now notice here, nowhere in what I have written will you see a 1 equals 1. I know that by now a lot of you are frustrated with losing marks for writing things like 1 equals 1. It's not false. I mean, obviously 1 is equal to 1. That is not a false statement. It's just not relevant. What you're trying to show is that T0 equals -2 to the 0 plus 0 times -2 to the 0. You are trying to prove an equation. Yes, you're right that both sides happen to be 1, but that's not the point. The point is you're proving T0 equals -2 to the 0 plus 0 times -2 to the 0. That's what you should be showing. And this way that I've written it demonstrates that. But writing 1 equals 1 doesn't have any relevance to this specific problem. It just tells you 1 equals 1, and I already knew that, right? Okay, so now for the next basis case, n equals 1. Just like the other one, just compute the left side. T1 is -4. Compute the right side. You get -4, and then just say, they are the same. Left-hand side equals right-hand side, and that's what you wanted to prove. So generally, if you're proving an equation by induction, compute the left side, compute the right side, show that they're the same. That's probably the best way to do the basis in pretty much every case where you're proving an actual equation like we are here. Okay, let's go to the inductive hypothesis. What should it say? We're using strong induction, okay? Now, I'm going to say let n be at least, well, what do you think? You think it should be 1? That's correct, okay? Because that is the last basis case that we proved. We already know it is true for all the n from 0 up to 1, right? So we can assume that it is true for all values from 0 up to 1. So I'm going to let n be at least 1, and I'm going to say assume that the formula tk equals -2 to the k plus k times -2 to the k is true for all k between 0 and n. And the important thing about this is that when I start my proof, after I've done my basis, I know that this inductive hypothesis statement is true for n equals 1. Okay, because it is the case that the formula holds for k equals 0 and k equals 1. Therefore, I can make this statement and it is true. And then I use that to prove the case n equals 2. And then at that point, I'm allowed to assume it's true for n equals 0, n equals 1, and n equals 2, and use that to prove n equals 3. And once I've done that, I can assume it's true for 0, 1, 2, and 3, and use that to prove n equals 4. And then now I know it's true for 0, 1, 2, 3, and 4. I can use that to prove n equals 5, and I haven't done anything that's like illegal. I haven't broken the rules. I'm using true statements to get other true statements, and therefore all of these statements are true. Okay, so this is what your inductive hypothesis should look like in a strong induction. Now, for the inductive step, at this point, we know that it's true for all numbers from 0 up to n. So the next one to do is n plus 1, right? I know it's true for up to n. What is the next case? It is the next thing after n, which is n plus 1. So I'm going to start by saying, what is Tn plus 1? Well, the thing is, n plus 1 is at least 2. And we know that if I have t with a subscript that is at least 2, I can write it in terms of the 2 previous values. That's what my recursive definition tells me. So I can write that Tn plus 1 is equal to -4 times Tn. That's the value that comes before Tn plus 1, minus 4 times Tn minus 1, because that's the thing that comes 2 steps before Tn plus 1. And crucially, the thing that allows me to do this is the fact that n plus 1 is at least 2. Why is n plus 1 at least 2? It's because n is at least 1, right? The n in the inductive hypothesis is still the same n that I'm using in the inductive step. So that n is at least 1, so therefore n plus 1 is at least 2, and I can use that to invoke the recursive definition. And now I'm good, because I can use the inductive hypothesis to just substitute for the previous values of Tn in this equation. So that's what I do. I just substitute these previous values using the inductive hypothesis. So I'm not going to say in words this whole equation here. It's kind of complicated. But the reason I'm allowed to do this is by IH, by the inductive hypothesis, because I know that the statement I'm trying to prove, the equation, is true for all k that is between 0 and n. Okay, so in particular, it's true for n, k equals n, and k equals n minus 1. Okay, so from here, it's just a lot of kind of annoying algebra, um, especially, okay, because it's got a lot of negatives in it and a lot of exponents, which I know that people sometimes get confused about. But really, there's nothing deep going on here. All I'm doing is collecting terms and things like that. And in the end, if you simplify everything, what you end up with is -2 to the power n plus 1 plus n plus 1 times -2 to the power n plus 1. And that is exactly what you wanted to prove. And so that's basically the whole proof. Of course, in induction, we also want you to tell us, what did you just prove? Okay, so please write a conclusion, and here's what it would say. So all it says is that Tn is equal to -2 to the n plus n times -2 to the n for all n at least 0. That's all, because that's all you proved, okay? Um, there is like some tendency that happens with these kinds of questions where people will start writing the recursive definition in the conclusion. Like they'll write, my conclusion is that Tn is equal to -4 times Tn minus 1 minus 4 times Tn minus 2. Or they'll write that and then they'll write a whole paragraph that then says in the end that, you know, maybe it says the right conclusion, but it's got all of this other stuff that just is not necessary. The question is, what did you prove? You proved that this sequence, for this sequence, Tn has the property that Tn is equal to -2 to the n plus n times -2 to the n for all n at least 0. You don't have to re-explain what Tn is. I mean, you don't have to re-explain the whole proof as part of the conclusion. That is not necessary, and that's not really helpful. And most likely you're going to just mess it up and lose some marks. So I really would recommend keep your conclusions simple and accurate. Okay, just say what you proved. Okay, so let's do this final proof. I want to prove that every positive integer can be written as a sum of distinct powers of 2. So let's just jump into it. We're doing a strong induction. We've got a basis case, n equals 1, which is just 2 to the 0. And so it can be written as a sum of powers of 2. Okay, let's go to the inductive hypothesis. We're doing strong induction. And so what we want to say is we want to let n be at least 1 and assume that all previous cases can be written as a power of 2, including n, so everything between 1 and n. For the inductive step, I'm going to divide it into two different cases based on whether n is even or n is odd, okay? It's not clear why you want to do this, perhaps, unless you kind of know what you're doing, but we'll see that this works out. So let's first assume that n is even. So then, by the inductive hypothesis, I can write n as a sum of distinct powers of 2. Right? Because the inductive hypothesis will allow me to do that for the value n, right? So we can say n is equal to 2 to the a1 plus 2 to the a2 plus ... up to 2 to the a sub r for some positive integers a or non-negative integers a1 up to ar, which we can assume are in increasing order. Now, since n is even, a1 cannot be 0. if a1 was 0, then 2 to the a1 would be 1. And then we could write n as 1 plus 2 times an integer, which would tell us that n is odd. So therefore, a1 is not equal to 0. That means that to express n plus 1 as a sum of powers of 2, I can take the expression for n and I can add 2 to the 0. Okay, so this case actually kind of looks like we're using weak induction, right? I'm just using the case n to get the case n plus 1. The tricky part comes in when we go to the case that n is odd. Okay, because this trick no longer works because, yeah, it's not going to work. But now the trick is to notice that if n is odd, then n plus 1 is even. So therefore, n plus 1 over 2 is an integer. And now we can apply the inductive hypothesis to the number n plus 1 over 2. So we can write it as being equal to 2 to the b1 plus 2 to the b2 dot 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 up to 2 to the bt, where b1 up to bt are non-negative integers. Now we just, so that's n plus 1 over 2 is equal to that. If we just multiply by 2, we can get n plus 1. We get that n plus 1 is equal to the same thing, but all the exponents are increased by 1. Okay, so then that completes the proof, and as a conclusion, we'll say that every integer n at least 1 can be written as a sum of powers of 2. Okay, so I went a bit faster through that one. It's a bit of a more advanced example, but it really shows why sometimes you really need strong induction, because you may need to go back to a previous case that is not just one case back. So in this example, to prove the case n plus 1, we use the case n plus 1 over 2, which is many steps backwards. Okay, so I hope that this helped for induction type questions, and I